All right. I know many of you are having problems with conversions of grams to mole or moles to gram or grams to molecules or grams to atoms. So I want to do a couple of problems here that highlight the mechanics of how to solve these type of problems. So for the first problem here, we have how many grams of carbon dioxide are needed to have exactly 3 times 10 to the second moles of carbon dioxide. So the key here is we know that we have actually given to us moles. We know exactly how many moles of carbon dioxide we have, and we are trying to get to grams. So there's our plan of action, and the next thing that should pop to your mind is what is the relationship between grams and moles? Well, anytime you see a calculation requiring moles to grams or grams to moles, um, molar mass is the term that should pop into your head. Molar mass. So what we need is the molar mass of carbon dioxide. And so the way we do that is we find out how much does 1 mole of carbon dioxide weigh. Well, if we have 1 mole of carbon dioxide, that means we have 1 mole of carbon and we have 2 moles of oxygen. So 1 mole of carbon, 2 moles of oxygen. So we go to the periodic table and we look up the molar mass for carbon. So if we go to the periodic table, we find that carbon weighs 12.011 grams per mole, and oxygen weighs 16.00 grams per mole. So if we multiply 1 times 12.011 grams per mole, the moles cancel out, and we have 12.011 grams. If we multiply 2 moles times 16 grams per mole, the moles cancel out, and we're left with 2 times 16, which is 32. So if we add that all together, we get 44.001 grams. That'll be good enough for us. 44.01 grams. So the molar mass of carbon dioxide can be written as 44.01 grams per mole. All right. So this is the key part of solving the problem, because what we're going to do now is we have exactly 3.0 times 10 to the second moles of carbon dioxide. We know that we want to get rid of the moles of carbon dioxide, and we want to be left with grams of carbon dioxide. So in our conversion factor here, we need grams in the numerator and moles in the denominator. Well, that's what the molar mass is. It's 44.01 grams per 1 mole of carbon dioxide. So on our calculators, the way we put this in on the calculator, and this may be where some of you are having problems, you would put in 3, and then you would find the exponential key on your calculator. It looks like this on a Texas Instrument calculator. It looks like this on a Sharp or Casio calculator. And then you would put in 2. That's all you need to do. 3 EE2. Now what that translates to is 3 times 10 to the second. So don't put a 10 in there. The EE key does all of this for you here. So we have 3 times 10 to the second, and we're going to multiply that by 44.01 grams per mole. And the moles cancel out here, so we're going to be left with grams. So take the 3 exponential second, multiply that by 44.01, and hit equals, and we get for an answer 13,203 grams. Now, of carbon dioxide. The problem with this answer, this is a rough answer. This is not the correct answer, in that when we go back to the original problem, we have 2 significant figures in 3.0 times 10 to the second moles. That's a measured quantity. So because it's measured and we have 4 significant figures in carbon dioxide's molar mass, we can only report 2 significant figures in our final answer. So the way we do that is we go 1, 2. We look at the number adjacent to those 2 significant figures, which is a 2. If this number is 5 or less, we round down. If it's 5 or greater, if it's less than 5, we round down. If it's 5 or greater, we round up. Since 2 is less than 5, my final answer would be something like 1,300 grams, or 13,000 grams, I should say, 13,000 grams. Now, I wouldn't leave it in that form. I think the zeros are ambiguous as to whether they're significant or not. So your best answer would be 1.3 times 10 to the 4th grams of, and always say what it's of carbon dioxide. All right? So 1.3 times 10 to the 4th grams. Again, you say, well, what happened to the 203? Well, these numbers here are not significant because the original question only had 2 significant figures for the moles of carbon dioxide. So I hope that helps you on this problem. Let's look at the next problem. This one's a little trickier. It says how many atoms are in 0.35 grams of carbon dioxide? Well, we're going to do the same thing. We know that 1 mole of carbon dioxide weighs exactly 44.01 grams to 4 significant figures. And the other thing that we're going to need is, because it's saying how many atoms, that tells us that we're probably going to use Avogadro's number here, which is 1 mole of anything, in this case 1 mole of atoms, equals 6.022 times 10 to the 23rd. And again, depending on how many significant figures you write for Avogadro's number, it can vary. Okay, so those are the 2 relationships we need to know. And again, atoms clues us into Avogadro's number, and then grams of carbon dioxide clues us into, in order for us to go from grams to atoms, we're going to have to go through moles, so we need the molar mass of carbon dioxide. So that's why we know we need this as well. So here is the hardest part of the problem, is coming up with the plan of action. We're going to start with what's given, grams of carbon dioxide. We're going to change that to moles of carbon dioxide. And then once we get to moles of carbon dioxide, we're going to convert that to molecules of carbon dioxide. And that would be generally where we would stop on this problem. But this problem doesn't say molecules of carbon dioxide. It emphasizes how many atoms are in there. So we're going to have to convert molecules of carbon dioxide into atoms in carbon dioxide. All right. Well, you say, well, where does that come from? Because we haven't talked about, we've talked about molar mass, we've talked about Avogadro's number, but how do you change molecules to atoms? Well, you know that for every 1 molecule of carbon dioxide, that is equal to 3 atoms. You say, well, how'd you get that? Well, carbon dioxide has 1 atom of carbon, and it has 2 atoms of oxygen. So if we add those together, we have 3 atoms in every molecule of carbon dioxide. So on the right here, we have the equalities that will eventually become the conversion factors. On the left, what we have here is the plan of action required to solve the problem. So between these 2 things, this is how we solve all chemistry problems. You have your equalities that become your conversion factors, and you have your plan of action of how to solve the problem. And that's the difficult part, is coming up with the plan of action, because if you don't know the equalities, you can't do the plan of action. So in the plan of action, what each one of these arrows represents is a conversion factor. So we're going to have 3 conversion factors in our problem here. So we're going to start with what's given, 0.35 grams of carbon dioxide. And the first thing we need to do is get rid of the grams and end up with moles of carbon dioxide. So we have moles per gram. Well, the only place we see that relationship is up here. We're taking this equality here, and we're actually dividing both sides by 44.01 grams. Now, you say, why did we do that? Well, I want moles per gram. There's my conversion factor. This side becomes 1, so that tells me this is a true conversion factor, because we know, like in math, that 7 times 1 is 7. So because this conversion factor equals 1, we know that we're not changing the amount that we have. All we're doing here is changing the units from grams to moles. And we know we set this up right because the grams of CO2 or carbon dioxide cancel out, and we have moles of carbon dioxide. So we have just finished this part of the problem. All right, so the next step is we need to convert from moles of carbon dioxide to molecules of carbon dioxide. So we need moles of carbon dioxide in the denominator, and we need molecules of carbon dioxide in the numerator. And I'm just going to use a shorthand notation for molecule. Now, be careful with that, because molecule and moles sometimes get confusing. So write at least a C after the E to say we're talking about molecules, not moles. So the relationship between molecules and moles of carbon dioxide is 1 mole of carbon dioxide means I have Avogadro's number of molecules of carbon dioxide. So what we really did here is we said 1 mole of carbon dioxide. Go back up here to this conversion, this equality. 1 mole of carbon dioxide means I have this many molecules of carbon dioxide. All right, so we divided both sides of this equality here by 1 mole, and that gave us this conversion factor. So we know we've set this up right because the moles of carbon dioxide cancel out, and we're left with molecules of carbon dioxide. So now we're at this point. So the last part of this calculation is they didn't ask for molecules of carbon dioxide, they asked for number of atoms. So for every 1 molecule of carbon dioxide, we have 3 atoms. 1 atom of carbon and 2 atoms of oxygen. So the molecules of carbon dioxide cancel out here, and what we have left is atoms of N carbon dioxide. So this is all set up. We now have proven that each one of these steps, so now it's just a matter of punching it out on the calculator. So on the calculator you would put in 0.35, you would divide that by 44.01, you would multiply by, again, be careful on how you put the Avogadro's number in the calculator. It's 6.022. Hit the exponential key on your calculator, the EE key, and then put in 23, and that takes care of the exponent here. And then we're going to multiply that by 3 because that's what we have in the numerator here, 3 atoms. We hit equals, and we get for an answer 1.4367 times 10 to the 22nd atoms. Now, again, this is a rough answer. Maybe your calculator put out more digits than this, but what we always have to go back to is how many significant figures was in the original question. Well, there's only 2. Now, if we look at these calculations, the 44.01 that you calculated for the molar mass of carbon dioxide, that's 4 significant figures. We're using 4 significant figures for Avogadro's number here. And then the 1 to 3 ratio here, that is a counted thing. That's got an infinite number of significant figures. So we should only have 2 significant figures in our final answer. So we look at the 1, we look at the 4, we look at the 3 adjacent to the 4. It's less than 5, so we round down. So my final answer is going to be 1.4 times 10 to the 22nd atoms. I hope this mini lecture has been helpful in showing you the mechanics of converting from grams to moles, or we could do the reverse, moles to grams, or in this case from grams to atoms. If you need further help, please post a question on the discussion board, and I will be glad to develop a mini lecture for you. Thank you.